So aside from hacks and things like that, we were talking about diffusion bonding, and it's limited on the low side temperature by the kinetics. It's just going to take too long in the furnace you can get great bonds, but it'll take you forever to do it because diffusion is slow at low temperatures. It's limited on the high side by grain growth. You'll get recrystallization across the interface, and you'll trap pores, and the pores are going to weaken the interface where you made your bond. So you're limited by this kind of 6/10 to 8/10 of the absolute melting point as an effective temperature to do it. Now, one variation on solid state diffusion bonding, where you're just doing two solids and there's no liquid, there's just pressure and temperature breaking down the asperities and dissolving away the oxides and other contaminants, is to use transient liquid phase bonding, which is actually, I guess, it's a registered trademark of Pratt & Whitney, even though, and they patented it in the early 70s, even though other people have been using it in their late 50s. And in fact, they went through a big patent case and they lost their patent rights on it. But nonetheless, trademarks are still trademarks. But the people still in the literature tend to forget that it's a registered trademark and call it transient liquid phase diffusion bonding. It starts out as a braze where you interpose a liquid, and that helps dissolve the contamination and gives you 100% area of contact. It ends up as a diffusion bond after only 1 or 2 hours. You diffuse away the low melting constituent, and you solidify by going across the phase diagram rather than down the phase diagram. Now, TLP bonding's interesting. Pratt & Whitney did get this patent, and it eventually was invalidated, but not by the first people who ever used the process. It turns out the Etruscans in about, I can't remember, it was 200 AD or 200 BC, basically were putting little gold beads on copper pots by using a TLP bonding technique, although they didn't trademark it, they didn't patent it. And when Pratt & Whitney filed their patent, they didn't file an infringement on their process, but they were actually, the artisans back in 200 BC or whenever it was, were putting little gold beads on copper pots with I believe is probably a tin-based solder, and the tin diffused away, and you end up bonding gold to copper. Now, some people believe that in about 2000 BC, King Tut, you know, whenever you see a picture of Egypt, you see this guy with the headdress and the stick for a beard or whatever. King Tut, or Tutankhamun, or whatever his name is, supposedly had his gold dagger in some museum somewhere, and it has little gold beads on it, and people think that was probably made by the same type of process that the Etruscans used. So even earlier than the Etruscans, in 2000 BC, people were using diffusion bonding, although they're not sure if they were using TLP bonding at that time. And they could be sure if they would just cut it open and do some metallography on it, but nobody has any interest in science, I guess, in these things. They just want to preserve the old sword. In any case, there's also, I've got some samples here of TLP bonds that have been made around here. One of my students a few years ago was studying the process. This is 2 pieces of copper, and the joint here is about 1.5 centimeters thick. This particular case, we were trying to find a way to make thicker diffusion bonded joints, because one of the things that people like to do, I didn't bring it, but I passed around some turbine blades before that have little cracks in them. And when you bring back a turbine blade, remember these things are worth on the order of $3,000 or $4,000 a piece. So if you can get another 5,000 hours out of one of these things of engine time, you've saved a lot of money. And so they'll develop little cracks in certain places, and they will essentially fill that with a bunch of powders, some of which are low melting, some of which are high melting, nickel-based powders, and pack that in there and put it in a furnace and kind of let the liquid braze those powders in there. And they try to make a good, essentially brazing of powders, but also partly a TLP bond. The problem with just packing powders is there's about 50% density if you just take powders. If you took sugar or salt or anything and just pour it in a beaker and measure its density, it's only about 50% of its theoretical density. Half of the space is just air between the particles. And even if you try to compact it under pressure, there's only so much pressure you can exert against the turbine blade, and you let things melt, you'll end up with some porosity left over. You always end up with 5 or 10% porosity, and that porosity is harmful to the final product. So my student was trying to figure out how to get rid of that porosity, and he finally came up with a technique. In this case, he just put copper powders, pure copper powders, between 2 copper platins, and he put a couple of silver foils on the interfaces, and then he infiltrated the silver into the copper. And essentially, if you're infiltrating the liquid all from one direction, you can sweep the porosity forward, if you will, or you end up pushing it in, and you get 100% density. And it's machined on the side, so you can see that it's solid. Now, the actual trick on this was not just that. The problem with infiltrating this stuff is if I've got a bunch of copper powders sitting here with other powders underneath, and I want to infiltrate silver liquid in between, if there was no reaction between silver and copper, then you could infiltrate this, you know, as far as you want in theory. But the problem is silver and copper form a nice eutectic phase diagram that looks something like this. There's the liquid, here's silver, here's copper. They melt it within 100 degrees of the same temperature. Actually, copper is a little bit higher. But in any case, here's your liquid, your eutectic temperature. And if this is your liquid composition, or actually if you start with pure silver, as the silver diffuses in, it's going to want to erode away. Copper will dissolve in silver, and silver will dissolve in copper. So it will erode away the particles. The liquid erosion is very rapid, and as this copper particle gets smaller, it basically falls down in between these other particles and it blocks the pores. And so you're only able to typically infiltrate maybe a half a millimeter or a millimeter. But that's infiltrated 1.5 centimeters in that particular case, mostly because he was just limited. It started out maybe 2.5 centimeters thick or 3 centimeters thick to make that and squeeze it down. The trick in that case was to coat each copper powder with a layer of nickel. It turns out silver and nickel are immiscible in each other. So silver will not erode the nickel, and so the silver will go in. However, you're at a high temperature, so over time, the nickel will diffuse into the copper because copper and nickel are soluble in each other. Once the nickel diffuses into the copper, now you've got a copper-nickel alloy, which the silver will dissolve into, and so you end up getting a transient liquid phase diffusion bond, and you use the nickel as a barrier layer, a transient barrier layer, to keep the erosion, the liquid metal erosion, from occurring too quickly. So you can now, with proper barrier layers, make a number of different types of TLP bonds, and this actually is. This is Inconel 625, so here's a nickel-based superalloy, and basically there's about a 3/4 of a centimeter gap here, which was a bunch of powders with some nickel boron, basically a TLP bond with that same liquid infiltration. And this next one, you have to you don't see the thing by just feeling it with your finger, but you can see the different coloration. That's a piece of titanium tensile specimen from the student's research. So different alloys you can fill big gaps and end up with 100% bond area. Another example of a problem, also another example of how people can sometimes lead you astray when you go out on a consulting project. I got a phone call from a company here on the North Shore one time, and they were having problems brazing molybdenum to copper. Now, molybdenum melts at like 2,900 centigrade or something like that, copper at 1,100. And they wanted to braise it. It was actually part of a radar system for the Navy's Aegis missile system. And basically, it's called a cross-field amplifier for a phased array radar system. And I don't know that much about that, except that this was a circular ring with copper slots, and the center had a hole in it with a little molybdenum circle. And basically what happens here to amplify the microwaves for the radar system, you have a very powerful pulsed electron beam that comes through this hole. And this is sort of like the microwave equivalent of a transistor. You want to take a small microwave source, small power microwave source, and turn it into a high power microwave source. And that means you've got to modulate electrons very, very rapidly at very high frequencies here. And so basically you put your small signal into the copper, which creates a magnetic field around the circle, and you put a very high power electron beam through here, and the magnetic field modulates those electrons pulsing through there, and it gives you a burst of the microwave frequency radiation that you want. So they call it cross field because you got a cross magnetic field and electric field coming through, and it's an amplifier because it's amplifying the microwave radiation. The problem here is that when you pulse this high power electron beam, it generates a lot of heat, and you have to have a high temperature material that won't melt. If you just had copper tips here, you'd melt off the copper tips and the thing wouldn't work. So they end up having to braise this in, and then eventually they'll machine it and slot it through on an EDM machine. And they'll end up with a bunch of fingers with a little molybdenum tip brazed to the copper here. Now, I guess this radar and other types of radar are based on this, are used when pilots, this is for the Aegis missile system, but it's also used when pilots are trying to fly nap of the earth. So if you're coming into Afghanistan or during the Gulf War, Iraq, or maybe next month Iraq or whatever, and you don't want to be flying, you can either fly very high where you hope that people can't hit you with the missile because they can't aim that accurately, but that's getting to be not true. Missiles can hit things further away with pretty good accuracy, or you can fly very low so they can't even pick you up on the radar system because you're flying nap of the earth. You're too close to the earth, and they can't see you coming in. The problem with that is there happen to be hills, and if you're going at Mach 1.5 or something like that, and you run into a hill, it can ruin your day. And so you have this radar that's supposed to be telling the aircraft where the hills are, so that you actually have some automatic controls so that the aircraft itself flies over the hills. And if you lose one of these little tips on the molybdenum, it destroys the symmetry of the whole thing, and I guess it destroys the radar signal that you're pulsing back and forth to measure this. So it's a pretty critical part of the system not to have the heat destroy these things and to have these things have good integrity. So anyway, they call me in and they tell me about this problem. They say, we're brazing these things with 82 gold, 8 nickel. 82 gold, 18 nickel. It turns out if you look at the phase diagram for gold nickel, it's a very simple phase diagram that's supposed to be the minimum point, but anyway, that comes together at 82% gold and 18% nickel. There's a low melting eutectic. That shouldn't go down that far, but anyway, right at this point. So this is liquid, solid, liquid plus solid, and another liquid plus solid over here. So it's even, in a sense, even simpler than the silver copper eutectic. And so this makes a great braze alloy if you're trying to braze at around I think it's 982 degrees centigrade or something like that. Makes a great braze alloy, except it's a little pricey, given the fact it's 82% gold. But in any case, they were using this. The problem, if you've got a molybdenum copper joint with this braze alloy, is with 18% nickel, you got copper up here, molybdenum down here. Molybdenum tends to form a oops, that's the wrong one, a nickel 3 molybdenum intermetallic that's brittle. And I mentioned before, one of the problems with diffusion bonding is brittle intermetallics. This is actually supposed to be a braze, and they were getting these brittle intermetallics, and so if you try to make one of these specimens and bend it, you get like a 5 or 10% bend before the molybdenum would just snap off. And that was a problem in terms of overall reliability. So it turns out, rather than using 18 gold, 8 nickel, or 82 gold, and 18 nickel, they decided to try, well actually they didn't tell me this. They said, well, how do we solve this problem? This is where they sandbagged me. They put me in a room with about 10 people and they explained all this problem to me and said, you know, how can we make a better joint? And I said, well, gee, you'd really like to have some sort of diffusion bond in here and even a transit liquid phase diffusion bond so that you could get rid of the intermetallics and end up with a braising process that you just hold in the furnace a little bit longer and end up with a diffusion bond that has lots of ductility. They said, well, how do you do that? I said, well, I don't know, just off the top of my head, I'd have to go back and look at phase diagrams and try to figure out what the metallurgy is and figure out what I can use. And after 2 hours of this kind of discussion, they said, well, could you write us up something on how you might go about doing this? I said, well, yeah, you know, kind of a little research proposal, okay? And they said, by the way, we did try something. And what they tried was a 37% gold. It was something like 3% nickel and 60% copper alloy, which is a commercial brazing alloy. And they had tried that braze alloy, and it turns out if you did a bend test, you could bend the whole thing 180 degrees on itself, and the copper would just stretch, and the molybdenum being stronger didn't deform, but you could bend it, the copper would stretch, and you got a beautiful joint with no intermetallics. And they said, you might just look at this and see, you know, why we're getting so much better behavior here. And by the way, the Navy doesn't like this because they think we're just changing it. It's a critical system, and they won't buy off. They think we're just trying to save money by using less gold. And so I went back to the lab and we polished one of these things and we looked at it. We couldn't find the braze joint. And then I started thinking about the metallurgy. Well, what they had done is the gold was diffusing into the copper because copper and gold form a nice continuous series, leaving enough copper behind. The nickel was low enough that you wouldn't form the nickel 3 molybdenum. With low enough nickel, there's not enough nickel left over to form that intermetallic. The thermodynamic activity becomes too low in the nickel. The gold diffuses away, left a TLP bond, and it was a perfect bond. So they had actually solved the problem. They didn't know it, and they did. Again, it was kind of like I talked about the transformers the other day with the lead tin solder, and they had actually solved the problem there. They just didn't know what to call it, and they needed a fancy name to tell the regulators, in this case the Navy. Actually, in the other case, it was also the Navy. Needed a fancy name to give it a fancy scientific name so that people could buy off and feel it was, you know, this is an improvement. We're going to TLP bonding as opposed to braising. And it's not really a cost reduction. So again, I wrote a letter. In this case, they had solved their own problem. But I wrote a letter because, remember, I gave you one definition of a consultant. And you know the other definition of a consultant, anyone who comes from more than 50 miles away. But the one I gave you was, I think, a better one. Someone who borrows your watch, tells you what time it is, and then keeps it. Usually the answers are right in the organization itself, if they just knew how to ask each other for the answers. So that's the cross-field amplifier and how they changed to a different braze system and ended up with the diffusion bond, which much better properties. Any questions on any of those things? Did you have a question? No, Chris, no. Okay. No, I thought you. Another thing is I call it activated diffusion bonding, and this is not what General Electric calls activated diffusion bonding. What General Electric calls activated diffusion bonding is TLP bonding, because Pratt & Whitney their competitor has a registered trademark on TLP bonding. So some parts of the literature use activated diffusion bonding for what I'm talking about, what I'm going to talk about right now. And basically, I mentioned before that you can have certain types of materials like aluminum or magnesium that have very refractory oxides. Difficult to get away from those oxides because they don't dissolve in the base metal, and you end up with a difficult to bond interface. Well, what you can do in many cases, for example, if I wanted to diffusion bond aluminum, I might plate it with tin, or I might plate it with zinc, or I could plate it with nickel and then put some copper on it and then put some tin on it or something like that and end up with a TLP bond with a copper interface. And we've done those types of things in the lab. But the example I was going to use here is actually from a paper by OBrien Rice and Olson in the Welding Journal back in 1976. And these guys worked at Rocky Flats, which is where they used to design atomic bombs and things like that. They wanted to bond at very low temperatures for some reason. Very high strength iron to very high strength iron. In fact, this iron was what we call a marging steel, and it had 180 KSI yield strength. So it was very high strength steel. But they had to join it with reasonable strength at very low temperatures because there were other parts in this whole system that couldn't see high temperatures. And they were able to achieve a bond by putting an inner layer of silver at the interface, a diffusion bond, at 400 degrees centigrade in 10 minutes and 20,000 psi bonding pressure. Now, 20,000 psi bonding pressure is a pretty high pressure. They don't melt silver at 400 degrees centigrade. It melts at around 971 or 972 or something like that centigrade. But 10 minutes is a pretty quick bonding time. And when they put this all together, they got 100 KSI bond strength. And really what they're doing is they had already plated the iron with the silver in a chemical process and then put this whole thing together and bonded silver to silver. Because silver to silver is an easy thing to bond. And the reason silver to silver is an easy thing to bond is silver dissolves oxygen easily. Plus, if you get to a little bit higher temperature, above about 200 degrees centigrade, silver oxide is no longer stable. Silver sulfide is. That's tarnish on silverware. But if you keep it from, if you plate it and you keep it away from an industrial environment, it's not going to tarnish very rapidly. And so you can basically squeeze this thing together under high pressure, short times, and they were able to get 100 KSI bond strength. What's unusual about that? You have a question? Yeah.
Yeah, the strength of silver is only like 20,000 psi.
Yeah. Okay. Well, that's part of the. That's the question. Okay. That's the problem. Is silver itself, pure silver, is relatively soft. Silver dinnerware or whatever is alloyed with copper to make it stronger. In fact, sterling silver is 7.5% copper and 92.5% silver. Actually, it doesn't have to be copper. It can be anything else. It just has to be 92.5% silver and anything else you want to put in there. But typically, they put copper in. Well, the reason that you get a higher strength here has to do with something that we call contact strengthening, that when you have two very strong materials and a thin, weak material in between, when you actually try to pull that apart in tension, the material in the center is supported, the soft material in the center is supported by the stronger material on either side. When we get to brazing, this becomes a very important way of strengthening in braze joints, and I'm going to do the one time in this course I ever solve a differential equation. I'll solve a differential equation for you just to prove I'm an MIT professor. And show you how you set up triaxial stresses in there. But essentially, you've got a material in between there that only has a strength of 20,000 psi, but when you pull it in tension, the whole joint behaves as if it has 100,000 psi strength. And so they were able to make whatever thing they needed for their weapons or whatever at relatively low temperatures and get a diffusion bond. You can do that in lots of other systems. Like I said, we've taken aluminum silicon carbide composites and plated them with tin or with copper, and then essentially diffusion bonded those types of things. Now I've got a copper interface, and copper is easy to diffusion bond. Tin, I could do a TLP bond, diffusion bond. against another piece of copper or something. So there's lots of ways to play games with the composition of the interface to change a material that generally is not very bondable into one that's bondable. Let's see if I got any other diffusion bonding stories, or anybody have any questions, thoughts? Yep.
I have a question. Every year it seems like somebody, after they take the course, wants to make a titanium bicycle.
Yeah.
Diffusion bond titanium bicycle. I mean, does that work?
It works if you got the money. Of course, people are paying $3,000 for titanium bicycles anyway, so I guess someone's got money, right? The problem, titanium is above 900 degrees centigrade. Titanium you can do a beautiful job with the diffusion bonding. One of the problems, which I'm not sure I mentioned very much or emphasized, in diffusion bonding, you have to have if you're going to do solid-solid without TLP, your interfaces have to be machined within about 1/1000th of an inch, and they have to be concentric. They have to be flat. Otherwise, your pressure is not going to be able to put them together. The problem with diffusion bonding a bicycle, you could do it, but now you're going to have all kinds of fancy knuckles where, in a bicycle you got 3 or 4 tubes coming together. How do you get pressure on those tubes? If it's all flat joints, you might be able to do it. So diffusion bonding is not the way you usually do a titanium bicycle. Typically, there is a shop up here in Cambridge that sells these $3,000 titanium bikes, and they do gas tungsten arc welding, which titanium does a beautiful job of gas tungsten arc welding too. But argon atmosphere, you can't, not a vacuum, but an argon atmosphere. You could do that, but that's basically just a variation of brazing. And it turns out they do that on titanium with copper nickel alloys. Okay, so you have titanium, you have a copper nickel alloy in between, and you'll end up with titanium over here. And nickel and copper will both diffuse into the titanium. It's not a true TLP bond because you always see the interface there. There's no interstitial diffuser in the titanium. We actually once tried to do very low temperature titanium bonding below 900 centigrade, and we actually used zinc as the interstitial diffuser, or not interstitial, but the low melting diffuser, and it actually could do some pretty good things. The problem was the zinc vaporized off at the same time. You had to do it in a vacuum and things. So vacuum processing makes a bike expensive. I mean, you gotta have a vacuum furnace. How do you get the pressure in there? If you're gonna do TLP, you might be able to just do brazing. If you're gonna do brazing, and you have tubes to tubes, you can put a tube inside a tube and get lots of braze area, just like on adhesive bonding, you're looking for lots of area. However, that thickens up the joint and makes things heavier. And I've yet to have anyone explain to me, and I've asked a number of times over the years, why taking an extra ½ pound off a bike makes a difference. Maybe if you're near the Tour de France, okay, but why an extra ½ pound off the bike makes a big difference, particularly when you start carrying another 2 pounds of water or something like that. Why are you so interested in doing this? But I mean, ever since I came to MIT and worked in joining, about every year I get someone who comes by and they want to make a graphite Kevlar epoxy bicycle, or they want to make a magnesium bicycle, or they want to make a titanium bicycle. And there's, they want lightweight structural materials. And I can understand why it's nice to have a lightweight bike, but why do you need to spend $3,000 to get the last pound out of there? Has anyone got an answer? I mean, I've never gotten a good answer, so no bicyclists here. Other than bicycles are I come to the conclusion, bicycles are to college students sort of like golf clubs are to post-50 white-collar men, okay? Golf clubs are to, you can sell anything to a golfer, okay? And you can charge a huge premium for it. And all you have to do is if you kind of wave your hand and say, well, this has got a higher modulus, and so therefore, the ball goes off faster and it's stiffer. And then someone else says, well, this has got a lower modulus and it stores more energy and then shoots the ball off. I mean, I hear, you know, if you read these how to get greater distance on your golf ball, if you want greater distance on your golf ball, hire Tiger Woods. I mean, he can do it. Why do you have to do it yourself? In any case, so yes, everybody wants to build something. But students, it's usually bicycles, a lightweight bicycle. And we've helped them build a couple, but I still don't understand it. I still don't understand why you pay $3,000 for a bicycle, but anyway. Chris would pay $3,000, but you pay $100,000 for a sports car too. So, but see, I wouldn't. You're just going to get a ticket, right? In any case, that's all I've got on diffusion bonding at the moment. It's an important process. It's an expensive process. We couldn't make a lot of aerospace components without it. It's been used for thousands of years, but it just doesn't apply across the board to everything. It's very limited in types of materials, types of temperatures, and mostly it's limited in the cost. And I don't know that there's a lot of great ways to lower the cost to get it down to automotive manufacture, not when it takes inherently a long time and expensive furnaces and things like that. So I want to move now to soldering, and soldering is an ancient process as well. This comes out of the American Welding Society soldering manual, and it's basically just a little cartoon of a soldering iron, a steel piece that would be plated with something that will wet the solder better, or the solder will wet the iron better if you put a layer of, if you tin plate the steel. So the solder's basically wetting the soldering iron because the solder is lead tin, and you plate the steel with tin, and now you have an iron tin intermetallic on the surface of this soldering iron. And you melt the solder, but you have to have something to get rid of the contamination on the surface. And so this is supposed to be representing, this layer right here is supposed to be the contamination on the surface, the oxide. This is typically copper if we're soldering copper, but we can solder other things. So you got contamination here. You have a flux, which in this case is trying to dissolve the contamination. And then you have a solder, a liquid metal typically, and there's a reason for that, rather than a liquid ceramic or something else. A low melting metal which wants to come in and displace the flux and leave solidified solder behind. So you're going to move in this direction. There's the arrow. Soldering iron is pulling heat by here. You've got temperature gradients. You've got a flux phase. You've got an oxide on the surface of the solder. You've got the solid on the surface of the base material. You've got the solid base material, typically copper. You've got solidified solder, and you've got liquid solder. It's a very, very complex process. But it's important in obviously lots of industries. Braising is a similar process in that we can do braising. You could do braising with an iron, but you don't usually do it with a flame because you need higher temperatures. But you can have fluxes, liquid metal going in between the other metal. Does anybody know the difference between solder and braising? Or another way to ask, did you read chapter 16? No. You haven't read chapter 16? Someone did, yes. It's just temperature. Absolutely, it's just temperature. The American Welding Society says that braising is a process that occurs above 800 degrees centigrade, or 800 degrees Fahrenheit. And so you got braising above that temperature. You have soldering below that temperature. The International Institute of Welding says that the temperature dividing the two is 425 degrees centigrade. If you convert the two, you'll find that they're both within about 10 degrees centigrade of each other. So why would there be this kind of arbitrary temperature? Anybody have an idea of why you just kind of arbitrarily call it soldering below this temperature and braising above the temperature? Aside from the fact, soldering actually goes back thousands of years. People were soldering things together in ancient times. Braising is a little bit more modern process. They use higher temperature filler metals and they started calling it brazing. However, to complicate things, has anyone ever done any silver soldering? Where you take a silver alloy and you make a joint? Well, silver soldering is actually silver brazing. We call it silver soldering, but it occurs above 425 centigrade, above 800 degrees Fahrenheit. It occurs about 1,000 degrees Fahrenheit, so silver soldering is actually silver brazing, just to complicate things. But there actually is a reason. And this actually comes out of the soldering manual, and they don't explain the reason. And someday I ought to get a better graph. But this says common alloy families for soldering and brazing. And they just got a little thermometer here, bulb. And they have what they call soft soldering down here. And this is the line at 800 degrees Fahrenheit. Above this temperature is brazing. Below this temperature is soldering. If you look at the different families, you have bismuth-based alloys. You can have indium bismuth. I think indium bismuth melts at, well, I don't know, indium tin melts at, indium melts at 156 C, and I think indium tin melts at 56 centigrade. So these are pretty low, you can get some pretty low melting solders. And if you go to, you're looking at all the low melting metals, if you go to gallium, gallium melts in your hand at something like 24 degrees centigrade. You probably shouldn't put it in your hand because it's kind of like mercury, it'll go through your skin and it's toxic. But aside from that, gallium will melt in your hand, not in your mouth. Actually, it will melt in your mouth too. Melts in your hand, no, it's, the phrase is melts in your mouth, not in your hand, right? In any case, gallium will melt in your hand and your mouth. So you got bismuth-based solders, you have indium-based solders, you have tin silver alloys, you have tin lead alloys, tin zinc alloys, zinc aluminum alloys, lead silver alloys. Tin lead alloys are typically the ones that we use for most of the electronic soldering, cadmium silver alloys, and cadmium zinc alloys. And so basically for soldering, we're using a bunch of low temperature metals, cadmium, indium, bismuth, lead, tin, zinc. You know, there are 10 or 12 low melting metals, and they tend to be solders. And there's a reason why we tend to use metals for solders, because metals have high surface energy. Metals flowing over the surface of a solid metal will end up giving metal-metal bonding, which gives a very low interfacial energy. If you look at the wetted surface of these things, if I've got a liquid on the surface and I've got my surface tensions between the three different phases, solid, liquid, and vapor, I want this surface tension between the solid and the liquid to be very small, okay? This interface needs to have a very low surface energy, very good atomic bonding, so metal-metal bonding across here. If I could flow a glass across the surface and I could have a glass-to-metal seal, and we make those things, but they don't flow anywhere near as well as a liquid metal solder. And typically the fluxes, and rather than when I have a flux, it's another liquid here. It's typically a ceramic, a chloride or an oxide or a fluoride type of salt that's molten. I don't have a vapor, I have another liquid, and the liquid solder has to be able to displace that flux. If it doesn't displace the flux, then you're not going to end up with the metal joint that you want for your solder. So it turns out we've got virtually all the low-cost, low-melting alloys in here. Gallium is not usually in here because, although you can make gallium solders, because it melts at almost too low a temperature. Mercury's not in here because of its toxicity and its low melting temperature. Although people have used mercury in cryogenic applications as a solder. Now, and gallium as well. Brazing is up here, and you've got your silver-based alloys. These are your silver solders. That's the problem with the terminology. Here's your aluminum silicon alloys. Here's copper phosphorus, silver manganese, copper zinc, copper gold, We talked about copper to gold braze alloys. And actually you have all kinds. There's a lot more than just that. However, there is something sort of unique. If you were to plot all the common elements in the periodic table, they either melt below 800 degrees Fahrenheit or significantly above, and even when you alloy them, there's almost nothing in nature among the common alloys that melts right around 800 degrees Fahrenheit. There's kind of a void right there. And so there is actually a natural break between soldering and brazing just because of what we have available in the periodic table. And so that is essentially one of the differences between soldering and brazing, is that we just don't have anything there. In fact, there are other applications. People have come to me over the years and they want a metal for some reason that melts at 800 degrees Fahrenheit. And I yank out this thing and say, you know, it doesn't exist. That's not to say you can't find something. I can find something in most cases. There are some aluminum zinc alloys, and you start adding tin and things. But among common things that we want to use that would work as solders or brazes very easily, there really is not much there. So that's why we have this somewhat artificial distinction. So that's enough for today. We'll do some more on
this. So you buy time with redundancy. If one fails, the other takes over. So when you look at this very closely spaced scheme, you realize that if you put a hole through it, a small hole, it's not that difficult. It just, the stress flows right around and is distributed. If you take the whole side out, it's another problem. So that's where you get the redundancy. What's left is how do you tie these systems together, this one and this one? Because if you don't support the box, if it folds in on itself, you're in trouble. So this is what they've done. This is your core. You can see the vertical members coming in here, the elevator shafts, the stairwells, and so on. You need to tie the core to the outside perimeter, and you do it with these bar joists, these open web joists, which are indicated by this pattern. The interesting aspect of this structure is these were prefabricated and lifted up in place, substantial. So there are some interesting structural aspects here. And you tie this part together with this part through this truss. This is just to support the truss. These things are about 60 feet long, which is very long for this type of structure, and about 3.5 feet deep. So it's a nesting of these trusses. You have to play some game to go around the corner. This is prefab, and then you mesh it in through there. All right? So what this does is, of course, is carry the 3,200 kips per floor, all right? This has to come on. You start with the floor load, which is in here. Some of it has to go into this core, and the rest of it has to go to the outside. And how you distribute that depends on how you connect the floor trusses to the walls. And they chose to simply support them. You saw that detail. It's just sitting there like a hinge. So literally half of it goes outside and the other half goes inside. So the exterior wall, this one, has two roles. The first role is to carry the wind, and the second one is to carry the gravity. Right? But in the case of when the accident occurred, the wind wasn't blowing, so it's really over-designed for gravity. It has a lot of flexibility. One more detail concerns the nature of the flooring system. This is not a very good sketch, but it does show these trusses. These are open web. This is open. This is the cross bracing. This is 60 feet long. It's connected to the outside edge, just sitting there on an angle, and it's bolted or welded. There's a little clip, a seat it sits on. This is the framing, the outside framing. You see this piece, the next one, and these, you bring it down, you pop it on top, and you bolt it up in through here. It's a very clever design. You're 2 stories or 3 stories high. You just bring it and assemble it up. So from a structural construction point of view, it's a very nice design. You see the connections here. All right? So this is an unusual system. This is very light. You have only 4.5 inches of concrete on the top. But this is where we're going to get into the problem. Diagram showing the nature of the prefabricated element. This is the unit that's made and lifted up 100 stories, plopped in place. But it sits on a beam here, so just plop it down. Then you connect it right in here. It has to be connected, tied down. Similar for the other end, because you have to make the outside wall participate with the core. And if it's just sitting there, it will just slide by. So you have to lock it down. All right? So the gravity load comes from here, goes out through here. Right? Now, if you lose that connection, you lose the ability to carry the floor load. So one plausible mechanism is to lose this support. This is a very, very, this is hypothetical, of course, but if you lose that, you lose the ability to carry this load. That's 3,200 kips. Okay? That comes down, it'll fall on the next one, break that connection, and down and down and down. Okay? So this one, there is a viscous damper in here, but this is not a moment-resisting connection that you'd see in a typical steel building. This is a simply supported, think about a pin on each end. You need it because if you lose that, the outside walls will come in, and also the inside wall can come out. So you lose the walls. So if you lose the diaphragm, you lose the walls, and you also get the gravity action. So my theory, which is only a theory, goes like this. We start with stage 1, all right? Connections. Now, there are 2, of course, because there's one side and the other side. So this is the exterior wall of the core columns. So if you lose this connection, this is going to fall, which would be 2 and down. It hits that floor, right, with an impact. Also, the force is not really vertical, it's inclined, so it's going to jog the system. And this is fairly heavy. This will break that connection. Here, stage 3. At the same time that it breaks the connection, it pulls the outside members in. Pull it, whoa. Pulls this in, see it? And breaks it. So it's tugging it in as it comes down. Whether this goes in or out, it depends on what's going on. But you can see the mechanism for having it come down on itself. Now it's parasitic. That is, when one breaks, it hits the second. Now what's coming down is 2 floors instead of 1, and this is going to accelerate the process, which is stage 4. Then it's over. It's literally free fall. I did compute the time required to drop something 800 feet. It's about 8 seconds. And that's about the time it took for the building to come down. But this is a mechanism that causes it to fall on top of itself. If you lost the one section of the outside wall, it would tend to fall over. You know, you could lose it that way, but that's not what happened here. It fell in on itself. So my theory is that we lost We lost the floor connection because of the nature of that design. I'm not criticizing the design. It was designed to be very lightweight, but you lost that, and that triggered the gravity mechanism. So the failure mechanism is driven by gravity. But then you have to really look at things in more detail. This is just me looking at the internet and conceptualizing. So let me now turn over to Professor Kausel, who will give you his view, and then we have Professor Bayuka with his view. Okay? And then we all get back together again and share our views once more.
Does this work? I prefer this loose. Can you hear me? Can anybody hear me? Okay, then I don't have to stand next to that thing there. All right, I'm Professor Kausel. I would like to talk briefly about three issues. One is design for extreme loads, not only for the World Trade Center, but in general. Then make some comments about why the structures collapsed. I mean, they collapsed in spectacular fashion. And finally, I would like to talk briefly about something which is now being talked about in our department, the design for redundant systems, basically providing extra safeties in buildings and structures that we design. Designing for extreme loads, and in particular in the case of the World Trade Center, we are dealing with a number of forces, hurricane winds, in excess of 100-mile-an-hour winds, 140 miles an hour. These generate enormous pressures. I mean, think of the World Trade Center as an enormous sail standing up there in Manhattan, 1,300 feet high, with wind pressures they are trying to top it over. These are enormous forces. And in the case of tall buildings like those, hurricane winds dominate the design in comparison to quakes. Quakes really for these very tall buildings are not really an issue. And if we do have earthquakes incidentally here in Boston, but they do not control the design of these very tall buildings. It is wind, the hurricane winds. The World Trade Center was also designed for impact loads, and you may have heard quoted that it was designed for the collision of a 707. It was also speculated that the 707 was smaller than the 767, which actually collided with the World Trade Center. But actually, that is not true. They're in size and weight, they're comparable. They're all, I mean, the 707, the normal was about 330,000 pounds. A 767 fully loaded takeoff weight is about 400,000 pounds. So the difference is not large. And the amount of fuel that this carried, one case 24,000 gallons, the other case 23,000 gallons, the difference was negligible. And by the way, 24,000 gallons represents more or less half of the weight of the aircraft, or a little bit less. So it is a very substantial part of the weight. Was it designed for that impact? Yes. Should it have resisted it? Yes. And you saw that actually the World Trade Center did resist the collision of both of these aircraft. Both towers resisted the collision, despite the fact that there was massive damage and lots of columns there at the point of impact that were basically deleted. And then they flew off the ground. However, when we say that it was designed for the collision of a 707, we need to qualify that, because the designers, and this is my opinion, but I'm almost certain of this, they never really designed for the massive explosion that followed immediately the collision. You had this enormous masses of fuel that then led to an explosion. And most certainly they did not design for the massive fire that would follow as a result of the jet fuel fire. I mean, office buildings are designed for office fires. You have what's called the fuel load of a building, which, as Bob mentioned, it has to do with how much flammable material you have, furniture and paper, et cetera, and that decides really how you design for these fire loads. And if you look at the experience of high-rise buildings in the United States, I mean, the safety record has been quite good. There have been office fires. Buildings have not collapsed. And in the future, I mean, if there were to be fires, most buildings are going to be withstanding, and we are not really terribly concerned that they may necessarily collapse. But most certainly, no building now and no building in the future will be designed to resist the enormous fire that was set up by these jet fuel fires. I mean, even the sprinkler systems were completely useless, really, to fight these fires. Now, if you look at the performance of these buildings, you see immediately that they performed admirably well. They resisted the initial impact. Lots of columns were deleted. They resisted the following explosion, a massive explosion. And then even after that, they stood there, one of them for about an hour, the other one nearly 2 hours. So in that sense, I mean, these performed admirably well. Yes, they ultimately collapsed, but at the same time, the fact that they stood for so long means that a good number of the people in the building could be evacuated. In fact, the majority of the people could be evacuated, and so the loss of life was not as high as it could have been. So this is designing for extreme loads. And then one of the issues there concerning the collapse of the buildings, we had, of course, all of us, I teach structural dynamics as one of the courses, and with my colleagues we had interesting discussions as to exactly why this collapse. I mean, how is it that the building began falling down? And I developed my models, they had their models, and interestingly, I developed a model that turns out to have been identical to a model that was proposed by Professor Stieniek-Bajant at the Northwestern University. We worked independently. He published it first on the web. Yes, so he has the priority. But the models were identical. This is one of them. There is another one. And I'm not going to spend time trying to explain this model to you. The only thing I wish to say is that if you regard this location here as the point of impact, because of the fire, the columns become, basically, this is an intense heat. The columns began becoming softer, basically like chewing gum, if you wish. I mean, as Bob mentioned also, the steel begins to lose stiffness, resistance, as you exceed 800,000 degrees Fahrenheit. And so basically these columns gave way and the upper part began falling onto the lower. Now the question is that enough really to trigger the collapse? And on the basis of this very simple model and one which I'm not showing you here, we can demonstrate that as soon as the upper part begins falling onto the lower part, and in other words, it falls from one floor height, from one to the next, the dynamic forces, the impact forces are so large, an order of magnitude larger than the design forces that the building can carry, that at that moment in time, the downward motion of the building becomes unstoppable. And then simply this whole thing keeps coming down without support. By the way, a number of people also in the press have been wondering, well, if this began failing, how come it didn't tip over like a tree? But actually, buildings are not like trees. I mean, in fact, well, for one thing, a tree is solid. A building, the typical building is mostly hollow. In fact, the building, the World Trade Center, and most buildings are virtually 90% air. 90% of the volume of the building is air, useful space, office space, elevator shafts, stairwells, etc. So it's open space, which means that of these 110 stories, only 10% is solid material. So if it collapses, these 110 stories get reduced to 10 stories or less because it spreads out. And of course, you have lots of rubble there at the bottom. So it's mostly empty space. And that, I mean, if you look at the mechanics of this, you can explain that this only can go down, it cannot tip over. And I don't want to really bother here with the exact details of that mechanics. However, I don't want to leave the impression that just because the floor fails, it has to continue failing all the way down in every case. There are some situations, for example, and this is one here, during the 1995 earthquake in Kobe in Japan, a number of buildings, and these are examples here, had one story that collapsed. In fact, for example, at the top here, the top floor collapsed and the rest of the building withstood the earthquake. In this particular case, the 5th floor collapsed. This is a 9-story building. And the bottom here, this is an 8-story building, and it lost here the 5th story. It concaved one another into another, but the system really not necessarily they continue. Sure enough, these are very different buildings. These are reinforced concrete buildings, are only 8-10 stories high, fairly light buildings. So the situations really are not immediately comparable. Whereas in the case of the World Trade Center, you had there a substantial portion, a very substantial weight above the field floor and with a tremendous weight. In fact, that's a disaster factor in the failure. Now, so that you get an impression of really of a few numbers here, we can look at the gravitational energy of a building. And so that you get the feeling for what this means when you think of a water dam and you have water behind the dam, that water has gravitational energy. And of course, you convert that by letting the water flow through the pumps, and then the pressure of the water and the gravitational energy gets converted into electrical energy. And by the same token, the World Trade Center has gravitational energy. The mass of the World Trade Center is approximately 500,000 tons, whether metric or English tons, it doesn't matter. I mean, these are approximate numbers. So it's 5 times 10 to the 8 kilograms. It has a height of, well, 1350. I wrote 14, but it's 1350 feet, 400 meters or so, and gravity and the metric system is that. And you can compute then the energy, the potential energy associated with this building. That works out to 10 to the 19 erg, which is a CGS, a metric unit, or if you wish, 278 megawatt hours. These are enormous numbers. To give you a comparison, this number represents approximately 1% of the energy released by a small atomic bomb. So 1% of this enormous potential energy, gravitational energy, while the building was collapsing, part of this energy was used up in destroying the material and basically disintegrating the material, rupturing and destroying the beams and columns, etc. And this is my estimate, by the way. I didn't have an instrument there measuring it. This is based basically on a post-mortem that I was doing. And the rest of this, the rest of that energy really converted to kinetic energy, basically things falling down. And then, of course, as these debris and the part of the building began hitting the ground, then you had then another effect where about 1/10 of 1%, a tiny fraction of that, was converted to seismic energy, basically waves that move through the ground. And they were recorded as earthquakes at the Lamont Observatory, Columbia University. It was estimated that this was an earthquake of magnitude 2, which is a tiny earthquake, actually. So only a very, very, very small fraction of this enormous